Tonight, I want you to take a breath, a deep one. Fill your lungs completely. Hold it. Now let it go. In the time it took you to do that, maybe 5 seconds, the universe expanded by roughly 250,000 miles. Every galaxy beyond our local group moved about 50 miles farther away from us. The fabric of space itself stretched, pulling everything apart, and you didn't feel a thing. You couldn't feel it. The room you're in right now didn't expand. Your body didn't stretch. The distance between your eyes and this screen remained exactly the same. But out there, beyond the reaches of gravity's grip, something is pulling the universe apart. Something invisible, something we don't understand, something that makes up nearly 70% of everything that exists. We call it dark energy, and it might be the most important thing in the universe that you've never thought about. Before we go further, if you find this kind of deep exploration valuable, a like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Look around the room you're in right now. Everything in this space is bound together. The walls hold their position. The furniture stays where you left it. If you have a cup of water on your desk, the water stays in the cup. Gravity keeps your feet on the floor. Electromagnetic forces hold the atoms in your body together. Chemical bonds prevent your cells from drifting apart. This room feels stable, permanent, the way things are. And in a very real sense, you're right. This room will remain this size for as long as it exists. The Earth beneath it will maintain its diameter. The distance from the Earth to the Moon will stay essentially constant. Our entire solar system, our galaxy, even our local group of galaxies, all of it is held together by gravity strongly enough to resist what's happening in the space beyond. But beyond that, beyond the reaches of gravitational binding, the universe is doing something strange, something that defies our intuition about how reality should work. The universe is not just expanding, it's accelerating, getting faster. And the force driving this acceleration, dark energy, is winning a war against every other force in nature. Think about your daily world, the streets you drive, the city you live in. Everything feels fixed in place, governed by rules you understand instinctively. You know that if you drop something, it falls. You know that things at rest tend to stay at rest. You know that without fuel, cars slow down and stop. These are the rules of the universe you experience. The universe of friction and gravity and inertia. The universe where everything eventually comes to rest, where energy dissipates, where things fall apart through entropy but stay together through structure. But there's another set of rules operating on a scale you can't see. Rules that only become apparent when you look at distances measured in millions and billions of light years. Rules that are, right now, determining the ultimate fate of everything that exists. Here's what you need to understand. The universe you experience every day, the universe of solid objects and stable distances, is a tiny exception in a cosmos governed by expansion. You're living in a gravitationally bound pocket, an island of stability in an ocean of space that's stretching faster and faster. And here's where things start to get strange. Let me take you back to 1998. Most of you watching this were either not born yet or you were living your lives with no idea that astronomers were about to overturn our understanding of reality. Two teams of scientists were doing something that should have been straightforward, measuring how fast the universe's expansion was slowing down. Notice I said slowing down. Everyone assumed the universe was decelerating. After all, the Big Bang was an explosive beginning, and explosions slow down. Throw a ball up in the air, it slows as it rises. The expansion of the universe should be the same. Gravity should be pulling everything back together, fighting against the initial expansion, gradually slowing it down. The teams were measuring distant supernovae, exploding stars that serve as cosmic distance markers. These particular supernovae, called Type 1a supernovae, are useful because they always explode with roughly the same brightness. This makes them standard candles. If you know how bright something actually is, and you measure how bright it appears from Earth, you can calculate how far away it is. The scientists expected to find that distant supernovae, which we're seeing as they were billions of years ago, were closer than they should be if the universe had been expanding at a constant rate. That would mean the expansion was slowing down, as expected. Instead, they found the opposite. The distant supernovae were farther away than they should be. The universe wasn't slowing down, it was speeding up. Let me help you understand why this was so shocking. Imagine you're driving down a highway and you take your foot off the gas. You expect the car to slow down. Instead, without any input from you, the car starts accelerating, faster and faster, with no fuel being added, no force you can identify, just spontaneous acceleration that defies your intuition about how things work. That's what these astronomers discovered. The universe is accelerating with no apparent source of energy. Or rather, the energy source is something we'd never detected before, something we still don't understand. They called it dark energy. Before 1998, we had a relatively simple picture of the universe. It started with the Big Bang 13.8 billion years ago. Everything began in an incredibly hot, dense state and began expanding. That expansion has continued ever since, but gravity has been fighting it, pulling matter back together, slowing the expansion down. We thought the universe's fate depended on how much matter it contained. If there was enough matter, gravity would eventually stop the expansion and pull everything back together in a big crunch. If there wasn't enough matter, the universe would expand forever but gradually slow down, asymptotically approaching some final expansion rate. We built our cosmology on matter and gravity, the stuff we could see, stars, galaxies, gas, dust, and the force that pulled it all together. We knew there was also dark matter, invisible mass that we could detect through its gravitational effects. Dark matter made up about 85% of the matter in the universe, but we could at least detect it indirectly. It was strange, but it fit within our framework. It was matter, it had gravity, it pulled things together. Then came 1998. The discovery of cosmic acceleration didn't just add a new piece to our understanding, it broke the puzzle. It revealed that the universe was playing by rules we'd never imagined. The astronomers who made this discovery, Saul Perlmutter, Brian Schmidt, and Adam Rees, were awarded the Nobel Prize in Physics in 2011. The Nobel Committee doesn't hand out prizes for small discoveries. This was revolutionary. This changed everything. Here's the current census of the universe, based on our best measurements. Dark energy, approximately 68% of all the energy in the universe. Dark matter, approximately 27% of all the energy in the universe. Normal matter, stars, planets, gas, dust, everything you've ever seen or touched, accounts for 5%. Read that again. Everything you've ever experienced, everything humans have ever observed throughout all history, everything made of atoms, accounts for 5%. 5%. The other 95% is stuff we don't understand. And most of that, more than 2/3 of reality, is dark energy. Let me help you feel this proportion. Imagine the entire universe is a 20-story building. Normal matter, protons, neutrons, electrons, all the atoms in all the stars and all the galaxies, occupies one floor, one single floor. Dark matter occupies about 5 floors. And dark energy? Dark energy fills the remaining 14 floors. It's the dominant component of reality, and we have almost no idea what it is. Here's what makes this even more disturbing. Dark energy isn't something that exists in a few exotic locations. It's everywhere. It permeates all of space uniformly. It's in this room with you right now. There's dark energy between your eyes and this screen. Dark energy inside your body. Dark energy woven into the fabric of space itself. Every cubic meter of empty space contains dark energy, and as the universe expands, creating more space, more dark energy comes into existence. The total amount of dark energy in the universe is increasing right now as you're listening to this. More space means more dark energy, means faster expansion, means more dark energy. It's a runaway process, and it's accelerating. Let's talk about what dark energy does, because this is where it gets truly strange. Gravity pulls things together. That's what it does. More precisely, gravity is the curvature of space-time caused by mass and energy, and objects move along the curved paths that mass creates. But the result is that things with mass attract each other, Planets orbit stars. Stars cluster into galaxies. Galaxies group into clusters. Gravity binds. Dark energy does the opposite. It pushes space apart. Or, more accurately, it causes space itself to expand, carrying everything with it. But the crucial difference is, gravity gets weaker with distance. If you double the distance between two objects, the gravitational force between them becomes 4 times weaker. Triple the distance, and it becomes 9 times weaker. Gravity follows an inverse square law. Dark energy doesn't get weaker with distance. Its density remains constant throughout space. Every cubic meter of empty space contains the same amount of dark energy, whether that space is here in our galaxy or in the void between galaxy clusters billions of light years away. This means that over short distances, gravity wins. It holds atoms together, holds planets in orbit, binds galaxies into clusters. But over vast distances, distances measured in hundreds of millions and billions of light years, dark energy dominates.
There's simply more space, and therefore more dark energy, creating more expansion. The result is a tug-of-war with a predetermined outcome. In the regions where gravity has established a strong hold, inside galaxies, within galaxy clusters, structure remains stable. But in the vast spaces between galaxy clusters, dark energy reigns supreme. And as the universe expands, those spaces grow larger, giving dark energy more room to operate, more leverage to pull things apart. The expansion is accelerating because dark energy's influence is growing. More space means more dark energy, means faster expansion, means more space. It's exponential growth, and we're living in the early stages of it. There's an equation that describes how the universe behaves. It's called the Friedmann equation, and it comes from Einstein's general relativity. This equation relates the expansion rate of the universe to its contents, matter, radiation, and something called the cosmological constant. The cosmological constant is represented by the Greek letter lambda, capital gamma. It's a term that Einstein added to his equations in 1917, then later removed, calling it his biggest blunder. The story goes that Einstein introduced lambda to keep the universe static because he, like everyone else at the time, assumed the universe was eternal and unchanging. When Edwin Hubble discovered that the universe was expanding, Einstein reportedly removed the cosmological constant, embarrassed that he tried to force his equations to match a wrong assumption about reality. But here's the twist. The cosmological constant, lambda, is back, and it might be exactly what dark energy is. Lambda represents the energy of empty space itself, vacuum energy. The quantum mechanical reality that empty space isn't actually empty. At the quantum level, particle-antiparticle pairs are constantly popping into existence and annihilating each other. The vacuum seethes with activity on scales so small we can't observe it directly, and that activity has energy associated with it. This vacuum energy could be what's driving the accelerated expansion. It would explain why dark energy's density remains constant as the universe expands, because it's a property of space itself, not something diluted by expansion. More space means more vacuum, means more dark energy. There's just one problem. When physicists try to calculate how much vacuum energy there should be based on quantum field theory, they get a number that's wrong by a factor of 10 to the power of 120. That's 1 followed by 120 zeros. It's not just wrong, it's the worst prediction in the history of physics. We're off by more than 100 orders of magnitude. So either our quantum theories are catastrophically wrong, or there's some mechanism we don't understand that cancels out almost all of the vacuum energy, leaving just the tiny amount we observe as dark energy. Neither possibility is comforting. This is called the cosmological constant problem, and it's one of the deepest mysteries in physics. Maybe dark energy isn't the cosmological constant. Maybe it's something else, something dynamic that changes over time. Physicists have proposed various alternatives. Quintessence, a hypothetical form of dark energy that varies in density over space and time.
Unlike the cosmological constant, which is truly constant, quintessence would be a field that pervades space but changes. The expansion rate would vary depending on the properties of this field. Modified gravity. Perhaps general relativity breaks down at cosmic scales. Maybe gravity doesn't work the way we think it does over distances of billions of light years. The accelerated expansion might not be caused by dark energy at all, but by gravity behaving differently than Einstein predicted. The problem is every alternative we've proposed either lacks supporting evidence or makes predictions that don't match observations. The simplest explanation, that dark energy is the cosmological constant, vacuum energy, a property of space itself, remains the best fit to the data. It just happens to create more theoretical problems than it solves. We're forced to accept that we live in a universe where 68% of reality is something we don't understand. That might be the energy of empty space, but if it is, our theories are wrong by 120 orders of magnitude. Let that sink in for a moment. We can calculate the orbits of planets to extraordinary precision. We can predict the behavior of subatomic particles. We can describe the first microseconds after the Big Bang. But we can't explain why the universe is accelerating, and our best guess is off by a factor that's incomprehensibly large. What we can do is measure dark energy's effects with increasing precision. We can observe how the universe's expansion rate has changed over time by looking at objects at different distances, which means at different times in cosmic history, since light takes time to travel to us. We've measured the cosmic microwave background, the afterglow of the Big Bang, with the Planck satellite. The tiny temperature variations in this ancient light tell us about the composition and geometry of the universe with remarkable accuracy. Dark energy, 68.3%, plus or minus about 1%. We've conducted massive surveys of galaxy positions, mapping how matter is distributed across cosmic scales. The pattern of clustering tells us about the balance between matter's tendency to clump under gravity and dark energy's tendency to smooth things out. The answer confirms dark energy is real and it's dominant. We've measured the distances to thousands of supernovae, refining the original 1998 discovery. The relationship between distance and redshift, how much the universe has expanded while light traveled from those explosions, precisely matches a universe dominated by dark energy. Every independent measurement points to the same conclusion. The universe is accelerating. Dark energy is real, and it makes up more than 2/3 of everything that exists. We can measure it. We can quantify it. We can predict how it affects the universe's expansion. We just can't explain what it is. Let me tell you what's going to happen. The universe is currently about 13.8 billion years old. We're living in what you might call the matter-dominated era, a time when matter, both normal and dark, still has significant influence on cosmic structure. Galaxies are still forming. Stars are still being born. The universe is dynamic, active, full of energy and light. But dark energy is winning, and as it does, the universe's fate becomes increasingly clear. Over the next tens of billions of years, galaxies beyond our local group will accelerate away from us. The expansion of space will carry them farther and farther, faster and faster. The light from those galaxies will become increasingly redshifted as space stretches the wavelengths. Eventually, that light will be shifted beyond the ability of any telescope to detect. One by one, galaxies will disappear from view. Not because they've died, but because the space between us and them is expanding so fast that light can no longer bridge the gap. The observational universe will shrink. The night sky will empty. In roughly 100 billion years, only our local cluster of gravitationally bound galaxies will remain visible. The Milky Way will have merged with Andromeda and a few other neighbors. Everything else will be gone, carried beyond the cosmic horizon by the accelerating expansion. Imagine you're an astronomer in that future era. You look out into the universe and see nothing, just your local galaxy group, alone in darkness. The cosmic microwave background will have been redshifted to such long wavelengths that it's undetectable. There will be no evidence of the Big Bang, no evidence that other galaxies ever existed, no way to determine that the universe is expanding, because everything you can observe is gravitationally bound. Future civilizations, if they exist, won't be able to discover cosmology. They won't know the universe's history. They won't understand where they came from. The evidence will be gone, hidden beyond a horizon that can never be crossed. We're living in a privileged time, a window of cosmic history when the evidence of the universe's nature is still accessible. A few 100 billion years from now, that window will have closed forever. But it might get worse. If dark energy is the cosmological constant, the universe will continue expanding forever at an accelerating rate. Structures held together by gravity will remain stable. Our local cluster will survive. Stars will eventually burn out. Galaxies will grow dark, but the fundamental structures will persist, locked in their gravitational embrace as the rest of the universe accelerates away. But if dark energy isn't constant, if it's something that strengthens over time, then we might be headed for something called the Big Rip. In this scenario, dark energy's density increases. Its repulsive effect grows stronger. Eventually, it becomes powerful enough to overcome not just the expansion-fighting pull of gravity between galaxy clusters, but the gravity holding galaxy clusters together. Then galaxies, then solar systems, then planets. In the final moments before the Big Rip, dark energy would become so strong that it would overcome the electromagnetic forces holding atoms together. Molecules would be torn apart, atoms would be ripped into their constituent particles. Space itself would be shredded.
Current observations suggest this isn't likely. Dark energy appears to behave like the cosmological constant, remaining steady rather than strengthening. But we can't rule it out completely. The measurements aren't precise enough. There's still room in the error bars for dark energy to be growing slowly. If the Big Rip is our fate, we have about 22 billion years before it happens. In the final year before the end, galaxy clusters would be torn apart. In the final months, galaxies would shred. In the final days, solar systems would dissolve. In the final minutes, planets would explode. In the final fraction of a second, atoms would cease to exist. Everything would end. All structure, all complexity, all information erased in a cosmic catastrophe caused by space itself tearing apart. This is unlikely, but it's possible. And the fact that it's possible tells you something about how little we understand dark energy. Here's something that keeps cosmologists awake at night. Light has a maximum speed, 186,282 miles per second. Nothing can travel faster through space. But space itself has no speed limit. Space can expand as fast as it wants, and in regions far enough away from us, it's expanding faster than light can cross it. This creates a cosmic horizon, a boundary beyond which we cannot see and can never reach, not because of technological limitations, but because of fundamental physics. Light from beyond this horizon will never reach us. The expansion of space carries those regions away faster than their light can travel toward us. This horizon is currently about 46 billion light-years away in any direction. That's the observable universe, but the actual universe, the total universe, might be far larger, perhaps infinite. We can never know. And here's what's disturbing. This horizon is shrinking. Not in distance, it's actually growing in physical size as the universe expands. But in terms of how much we can observe, it's shrinking. Galaxies that are visible to us now will eventually cross beyond the horizon and disappear. The observable universe is becoming less observable over time. We are fundamentally isolated, trapped in an ever-shrinking bubble of observability, surrounded by a universe we can never reach, never explore, never contact. Any civilizations that exist in galaxies beyond our local group are already unreachable. Even traveling at the speed of light, we could never get there. The space between us is expanding too fast, and it's only going to get worse.
If there are other civilizations out there wondering if they're alone, we're separated from them by an unbridgeable gulf. Not just distance, but expanding space that makes contact impossible. Forever. Let's return to the most disturbing aspect of all this. We have no idea why dark energy has the value it does. The observed density of dark energy is approximately 10 to the power of -9 joules per cubic meter. That's a tiny number. For comparison, the average density of matter in the universe is about 10 to the power of -27 kilograms per cubic meter. Dark energy dominates, but it's still incredibly dilute. The problem is that quantum field theory predicts vacuum energy should be vastly larger, some 120 orders of magnitude larger. If that were true, the universe would have expanded so rapidly in its first instant that no structures could ever have formed. No atoms, no stars, no galaxies, no life. Instead, we have exactly the right amount of dark energy to allow structures to form and persist for billions of years while still driving accelerated expansion. It's the Goldilocks problem. Not too much, not too little, but just right. This has led some physicists to invoke the anthropic principle. We observe the value of dark energy that we do because if it were significantly different, we wouldn't exist to observe it. Universes with too much dark energy never form stars. Universes with too little might collapse before life can develop. We exist in a universe fine-tuned for our existence. This explanation makes many physicists deeply uncomfortable. It feels like giving up on finding a deeper reason. It suggests that the answer to why does dark energy have this value is simply because if it didn't, we wouldn't be here to ask. Some take this further, proposing that there might be many universes, a multiverse, each with different values of fundamental constants, including dark energy. We happen to exist in one of the rare universes where the value allows for complexity and life. But this isn't testable. It doesn't even qualify as science. We're grasping for explanations and finding only deeper mysteries. Let me be clear about the depth of our ignorance. We don't know what dark energy is. Is it vacuum energy, a new field, modified gravity, something else entirely? We don't know if it's constant or changing. Current observations suggest it's steady, but we can't rule out slow variation. We don't know why it has the value it does. The cosmological constant problem remains unsolved. We don't know if our theories are fundamentally wrong. Maybe general relativity breaks down at cosmic scales in ways we haven't anticipated. We don't know what this means for quantum mechanics. The cosmological constant problem suggests a deep conflict between general relativity and quantum field theory. We don't know the ultimate fate of the universe with certainty. Will expansion continue forever? Will dark energy change? Is the Big Rip possible? These aren't small gaps in our knowledge. These are fundamental questions about the nature of reality, and we don't have good answers. We have measurements, we have observations, we have models that fit the data, but we don't have understanding. But here's what we do know. We know how to measure the universe. We've developed techniques of extraordinary precision to probe cosmic distances and expansion rates. We can map the universe's history from the Big Bang to the present with remarkable accuracy. We know that the universe is comprehensible. Even though we don't understand dark energy, we can quantify its effects. We can make predictions that match observations. We can test our models against reality. The universe follows rules, even if we don't fully grasp them yet. We know that ignorance is temporary. Every mystery we've ever encountered in physics has eventually yielded to human curiosity and ingenuity. Atoms were mysterious. Radioactivity was mysterious. Quantum mechanics seemed impossible. General relativity defied intuition, and yet we figured them all out. Dark energy might be the deepest mystery we've ever faced, but that doesn't mean it's unsolvable. There's something profound about living in a time when we can ask these questions, when we can look at the universe and realize that most of it is something we don't understand. Think about what that means. In the year 1900, physicists thought they'd figured out almost everything. Classical mechanics, electromagnetics, thermodynamics, the major frameworks were complete. Lord Kelvin famously said there were just 2 clouds on the horizon of physics, minor problems that would surely be resolved soon. Those two clouds turned out to be quantum mechanics and relativity. They revolutionized our understanding of reality. They opened up entire new fields of physics. They led to technologies that transformed civilization. We're in a similar position now. We thought we understood the universe's components, matter and energy, governed by gravity and the other fundamental forces. Now we've discovered that 95% of the universe is stuff we don't understand, dark matter and dark energy. This isn't a failure, it's an opportunity. We're standing at the edge of a revolution in physics that might be as profound as quantum mechanics or relativity. We don't know what dark energy is, but finding out might require new physics, new principles, new ways of thinking about reality. The mysteries are what makes science exciting. Let me bring this back to where we started, back to you, sitting in your room reading these words. The space around you is filled with dark energy. It's everywhere, uniform, unchanging in density. It's pulling the universe apart, but on scales so vast that you'll never feel it. The Earth isn't expanding. Your body isn't stretching. The room you're in remains stable. You're protected by gravity. The electromagnetic forces holding your atoms together are vastly stronger than dark energy's effect on human scales. You're safe in your gravitationally bound pocket of the universe. But out there, beyond the local structures, dark energy is winning. The universe is expanding faster every moment. Galaxies are accelerating farther away. The cosmos is growing larger, emptier, darker. And you're here, aware, thinking, part of the universe that can contemplate itself. That's extraordinary. You're made of atoms forged in stars that died billions of years ago. The carbon in your body, the oxygen you breathe, the iron in your blood, all created in stellar cores and scattered across space by supernovae. You're made of the universe, and you can think about the universe. You can ask why it's accelerating and what that means for the future. Dark energy might be pulling everything apart. That's true. The isolation is real. The mysteries are profound. The fate might be isolation or ripping or something else entirely. But right now, in this moment, you're alive in a universe filled with light and structure and complexity. You're conscious in a reality that can produce consciousness. You're capable of understanding in a reality that can be understood at least partially, at least enough to know that we don't know everything. That's not nothing. That's everything.
Tonight, if it's clear where you are, go outside and look up. Find a dark place, away from city lights if you can. Let your eyes adjust. Watch the stars appear, more and more of them as your vision adapts to the darkness. Every point of light you see is gravitationally bound to our galaxy or our local group. These are the stars and galaxies that will remain visible even as the universe expands. These are our cosmic neighborhood, the structures that gravity holds together against dark energy's pull. But beyond what you can see with your naked eye, telescopes reveal billions of galaxies. Most of them are already accelerating away from us, caught in dark energy's grip. The space between us and them is stretching, pulling them farther, faster, beyond any possibility of contact or exploration. And yet their light is still reaching us. Photons that left those galaxies millions or billions of years ago, crossing vast distances of expanding space, arriving tonight at your eyes. Ancient light, carrying information about the universe's past, about how things were when space was smaller and structures were closer together. You're receiving messages from the past. You're seeing the universe not as it is, but as it was. And that light is telling you something profound. The universe was different then, smaller, slower, less dominated by dark energy. We're watching the universe's history unfold in the light of distant galaxies. We're seeing the transition from a matter-dominated cosmos to a dark energy-dominated one. We're witnessing the acceleration in real time, or rather in ancient time, preserved in light that took eons to reach us. Look at the stars. Remember that you're seeing a universe in transition, a cosmos being pulled apart by a force we don't understand, a reality where 68% of everything is mystery. And remember that you're here to witness it. That's the gift of consciousness.
Not just to exist, but to know that you exist. Not just to observe the universe, but to comprehend what you're observing, at least partially, at least enough to recognize the profound strangeness of it all. Dark energy is real. The acceleration is measured. The fate might be isolation or ripping or something else entirely. But tonight the stars are still shining. The universe is still comprehensible, and you're still here, capable of wonder. That's enough. Thank you for taking this journey with me into one of physics' deepest mysteries. If you found this exploration valuable, a like or subscribe helps me continue making these deep dives into the nature of reality. And remember, every time you look up at the night sky from now on, you'll know something that changes how you see those stars. You'll know that the space between them is expanding, that dark energy is pulling everything apart, that we're living in a brief window of cosmic history when we can still see evidence of the universe's true nature. The universe is tearing itself apart, but it hasn't finished yet, and you're here to witness it. Good night, and may you never look at the darkness between the stars the same way again. Every second you exist, the universe expands by 250,000 miles. Every breath you take, galaxies accelerate farther into the void. This isn't metaphor, it's measurement, it's reality, and now you know.